everybody. In this video, I'm going to be going over circles quiz number 2. So in the first question, we're asked to find the length of AP, and we are told that AP is tangent to circle O. So the first thing I'm going to keep in mind is that O is the center of the circle, since this is called circle O. And from O to point B, we can consider that a radius of the circle because a radius is a segment that starts at the center of the circle and goes to any point on that circle. So if this is 7 over here, I know that all radii of the same circle are congruent. So OA also has a length of 7 as well. I do know that when a tangent to a circle meets a radii, or radius, I should say, it forms a right angle. So since I know that AP is tangent to the circle and OA is a radius, they do form a right angle where they meet. So now I know I have a right triangle, and I can use the Pythagorean theorem in order to find the missing side length AP. So we know the hypotenuse. The hypotenuse is 18 plus 7. Let me get my calculator ready to go for the rest of this. There we go. And this 25 represents the hypotenuse because it's opposite from the 90-degree angle. So I can do 7 squared, that's one of the legs, plus b squared, we're finding the other leg, is equal to 25 squared. 25 is c because that's the hypotenuse. So we have 49 plus b squared is equal to 25 squared, which is 625. We're going to subtract 49 from both sides, and I get 576. Let me take the square root of that in my calculator, and I get that b is equal to 24. And that represents the missing side of the right triangle, which is AP, which is what we were looking for. It is 24. Okay, in number 2, we are told that AC is tangent to circle O at point A and to circle P at point C. And we are given a bunch of measurements here to work with. And our goal is to find the length of BC. This one's actually a lot simpler than it appears to be. So I do know that segment BC is tangent to circle P, and I know that CP is a radius of circle P. So where a tangent to the circle and a radius meet, they form a right angle. Over here, the same thing can be said. We have a tangent to the circle, and we have a radius of the circle. When a tangent to the circle and a radius meet, they form a right angle. I also see congruent vertical angles. So from here, I know the two triangles are similar to each other by AA. Once I know that the two triangles are similar, I know that the corresponding sides are proportional. So I can set up a proportion to find the missing side of the bigger triangle. So if I'm going to set up my proportion as small over big. And once again, there's multiple ways to set it up. This is just the way I'm going to set it up. So I'm going to take a side from small triangle, that's 4, and put it over its corresponding side from big triangle, that's 10. Let me take the other side from small triangle and put it over its corresponding side from big triangle. From here, I'm going to cross multiply. I have 4x is equal to 50. On my calculator, if I do 50 divided by 4, I get that x is equal to 12.5. So that is the correct answer here. Okay, for number 3, we are asked to find the length of PS. So we're finding the length of a segment. We're given that PS is x. We're given that PQ is 3. And we're given that PR from P to R is x plus 18. Now, remember, whenever we are talking about segment lengths and we're dealing with segments that are partially or wholly outside of the circle, we use our rule that we learned about in class, whole times outside equals whole times outside. So taking a look at the tangent to the circle that we have here, the whole thing is represented as x, and the entire tangent is located outside the circle. So the outside part of the tangent would also be x, since its whole and its outside part are the same thing. The whole secant is represented as x plus 18. And the outside part of the secant, the part that's outside the circle, is just 3. So I have x squared is equal to, distributing the 3, I have 3x plus, let me do 18 times 3 on my calculator, I get 54. So I already see that I have a quadratic. That means I have an equation where the highest exponent is 2. There's nothing I can combine anymore. Nothing is a like term. So I'm going to have to factor here the solve. What I'm going to do is I'm going to move everything over to one side of the equal sign so I can have it equal to 0, and then I can factor. So when I'm factoring, I'm looking for two factors of negative 54 that add up to give me negative 3. So basically, I'm looking for two numbers that multiply to give me negative 54 and that add to give me negative 3. The numbers that come to my mind are 9 and 6 that multiply to give 54. So one of them has to be a negative to give us a negative product. And since when you add them, it should be negative, the bigger one should be negative. So that should be negative 9 and positive 6. Let me just double check that. 9 times 6, that is 54. So negative 9 times positive 6 is negative 54. And if I add negative 9 and 6 together, I do get negative 3. So that is what I'm looking for. So we have two solutions. We have x is equal to 9, and we have x is equal to negative 6. Since we're talking about a segment length, it doesn't make sense that it would be negative, then we wouldn't be able to see it in the diagram. So often in geometry, we reject the negative solution. So we have that x is equal to 9. And since x is PS, that's 9. That is what we're looking for. In number 4, we are told that AE is 16, EB is 4, and we are looking for CD. So in the question, they give us the key. Diameter AB is perpendicular to chord CD. When we have a diameter that is perpendicular to a chord, we know that it bisects that chord. So I can represent each part of the chord as the same thing. Since I don't know what each part is, I'll represent it as X. I do know that the chord is being bisected. That's why I'm able to do that, because we have a diameter perpendicular to a chord. It means it bisects it. Okay, so now I can do the part of this chord, which is 16, times the other part of that chord, which is 4, is equal to the part of this chord, which is X, times the other part of that chord, which is X. Remember, when we have segments inside the circle, we can't use whole times outside equals whole times outside because nothing is outside the circle. That wouldn't make sense. We wouldn't have anything to plug in. So when we have segments inside the circle that we want to find the length of, we use the product of each part of one segment is equal to the product of each part of the other segment. On my calculator, 16 times 4 is 64. And the square root of 64 is 8. Oh, 8 is x. There's two of them. We're looking for the whole thing CD. So that's 8 plus 8. That's 16. 16 is our correct answer. We weren't looking for x. We were looking for the whole CD. Okay. Number 5 is pretty easy. Whenever we have a quadrilateral that is inscribed in a circle, we have a special name for that. That's called a cyclic quadrilateral. And one special property of cyclic quadrilaterals is that their opposite angles are supplementary. So any two opposite angles in any cyclic quadrilateral, and any quadrilateral inscribed in the circle, are going to be supplementary. So that's J and M will be supplementary to each other. P and U will be supplementary to each other. In the diagram below, circle O is inscribed in triangle ABC. so that the circle is tangent to AB at F, to BC at E, and to AC at D. If AF equals to FB equals to 5, and DC is 7, find the perimeter of triangle ABC. So remember, we have a theorem that says if two tangents are drawn from the same external point, those two tangents are congruent. AF and AD are both tangent to circle O, and they're coming out of point A, so they're congruent to each other. If one is 5, the other is 5. Same thing over here. These segments here are both tangent to the circle and coming from the same point B. So they're congruent to each other. If one is 5, the other is 5. These two segments come out of the same point and are tangent to the circle. So they're congruent. If one is 7, the other is 7. Adding everything up, that's 7 2 times and 5 4 times. And that gives us 34 for the perimeter. 14 plus 20 is 34. Here we have an area of a sector question, and it's pretty simple because it's in degrees, not in radians, so we don't even have to worry about radians here. This is all in degrees. I'm going to set up my proportion. Area of a sector over whole area of the circle is equal to central angle over all the central angles, which is 360 degrees. We're looking for the area of the sector. The area of the circle can be found using pi r squared of the whole circle. The radius is 8, so plugging that in, that would be pi 8 squared, which is 64 pi. A lot of the people were using circumference here instead. The central angle is given to us as 60 degrees. Over the total central angles, that's 360. From here, we can cross multiply. We have 360x is equal to 64 times 60. Let me do that on my calculator. I got 3840 pi. Remember that pi, when we multiply it, that's still attached. The question does not say the round, so my answer is going to be in terms of pi. So to get the x by itself, I'm just going to divide both sides by 360. So in my calculator, I'm going to do 3840 divided by 360. And I get like 10.666666667. I'm going to convert it to a fraction because I'm not sure if it keeps going on beyond that or if that's actually where it ends in the calculator. So converting it to a fraction by hitting math, enter, enter on my calculator, I have 32 over 3 pi for the area of the sector. And our units are inches, so I'm going to write inches squared. Okay, moving forward. We know that dA is 56, dB is 112, and the ratio of AC to CV is 3 to 1. So here would be the 3 part, that's AC, I'll represent it as 3x. And here would be the 1 part, that's CB, I'll represent it as 1x or just x. So the first thing that we need to find is the measurement of this angle over here. In order to find the measurement of that vertical angle, I need to take half the sum of the intercepted arcs from the two vertical angles. I need this arc in order to do that. So I'm going to first set up an equation to find the arcs. So I know that all the arcs of a circle should add up to 360. So I'm going to do 56 plus 112 plus 3x plus x is equal to 360. Combining my like terms, I have 56 plus 112, that is 168, plus 4x is equal to 360. Quickly solving, 360 minus 168 is 192. And then dividing by 4 to get the x by itself, we have x is equal to 48 degrees. So BC, that arc is 48 degrees. And just in case we need it for later, if we wanted to find arc AC, that would be 48 times 3. And that is 144 degrees. Okay, so to find CEB, I'll put a little 1 here. to find CEB, we're going to take half the sum of the intercepted arcs. Remember, the vertical angle is equal to half the sum of its intercepted arcs. So half of 48 plus 56. In my calculator, I'm going to do that. 48 plus 56 divided by 2, and I get 52 degrees. So I'm going to put that in here for CEB. That is 52 degrees. Okay, moving on to the second thing we need to find. We need to find the measure of angle F right over here. The angle F is an outside angle. It's an angle formed by a tangent and a secant, but it's an outside angle. And we know whenever we're finding the measurement of an outside angle, we're going to take half the difference of the intercepted arcs. Half big arc minus small arc. So big arc here, if we look at where this opens up to, it hits point A, and here it hits point B. So arc AB is our large intercepted arc. So that consists of 144 degrees plus 48 degrees. So on my calculator, I'm going to add those together. So the big intercepted arc altogether is 192 degrees. So we're going to take half 192 minus the small intercepted arc. If we follow here, it hits D as well, and it hits B. So DB is the small intercepted arc. That's 112. On my calculator, I'm going to do 192 minus 112, and remember to divide that by 2, and I get 40 degrees. That's it. That's all we have to do. And then finally, the last thing that we need to find, I'll label it as 3, is DAC. DAC is right over here. DAC is an inscribed angle, and if we check out what arc it opens up to point D here, and following it over here to C. So its intercepted arc is DBC, which is made up of 112 plus 48. My calculator, 112 plus 48 is 160. So the intercepted arc for that inscribed angle is 160. We know that inscribed angles are half the measure of their intercepted arcs. So if this is 160, half of that would be 80. And I can write that work down here. Half of 160 equals to 80. And there we have it. That's everything that we needed to find. That wasn't so bad. Okay, moving along here to the proof. So first I will set it up and plan it out, and then I will actually write up the proof. So there are a bunch of ways to do it, but we are proving that two angles in the two triangles, so angle AOP, this angle over here, and angle BOP, this angle over here, are congruent. Notice how they are corresponding angles of the two triangles. So you might have figured out that ultimately, to prove that corresponding angles of two triangles are congruent, we're going to be using CPCTC. That's for corresponding sides or angles being congruent in two triangles. Before we can use CPCTC, we do need to prove the triangle's congruent. So we're not looking for AA here. This is not similarity. We're not proving a proportion. We're not proving a product. We're trying to use CPCTC, so we need to prove the triangle's congruent to each other. So already I see a shared side. That might help. I'm going to mark that. I see AO and OB. They are radii of the circle. That's given to us that they're radii of the circle. And I know that all radii of the same circle are congruent to each other. I also see over here that we have two tangents to the circle drawn from the same external point. So we know that they're congruent to each other when we have two tangents to a circle drawn from the same external point. So already I see I can use SSS. Some people were trying to use HL, and you can use HL, but a big thing I was seeing when people were trying to use HL is people identified that these angles were right angles because they were angles formed by a radius and a tangent when they meet. But what a lot of people were not recognizing is that in order to use HL in your proof, it's not enough to just say these angles are right angles and explain why. You also have to say the triangles themselves, triangle AOP and triangle BOP, are right triangles. And your reason could be a triangle with a right angle is a right triangle. But in order to use HL, since it is specifically for right triangles, you do need to state that you do have right triangles in order to use it. Another thing that people were doing with HL that was incorrect is people were trying to prove HL without having hypotenuses. Part of HL is the H, and H stands for hypotenuse. So make sure that you do have the hypotenuse if you are using HL. Okay, so I'm going to erase everything that I am not using. And I'm going to just write up my proof really, really quickly. I don't think I need to pause the video to do this. I think it'll be pretty quick. I'm not going to write up my givens just to save time in this video, but you should. You will get points off on the Regents exam if you don't write down all your givens. You don't get points for writing down the givens, but you do lose points for not having them. So please make sure that you have them on the Regents exam. I'm going to mention OP is congruent to itself. That is the reflexive property or postulate, same thing. I'm going to mention AO congruent to BO, and we know that because all radii of a circle are congruent. Lastly, we need AP congruent to BP, and we just spoke about how if two tangents to a circle are drawn from the same external point, they are congruent. So that's what we have here. We had two tangents to the circle drawn from the same external point P, and that's how we knew they were congruent to each other. Okay, now we can say the triangles are congruent to each other. So triangle AOP is congruent to triangle. Let me put the corresponding parts in order. A corresponds to B, O corresponds to itself, and P corresponds to itself. And I did that here by SSS. It is also possible to do this by both SAS if you use the right angles, or by HL if you stated first that your triangles were right triangles. So for HL, once again, you would have to first state that you have right angles and how you know that. And then after that, you would have to state that your triangles are right triangles and how you know that. So HL adds an extra step because it is specifically for right triangles. So you do need to state that you do have right triangles. And then finally, now that we know the triangles are congruent to each other, we know that the angles AOP and BOP are congruent to each other. And that is due to CP/CPC. Corresponding parts of congruent triangles are congruent. Moving along to the last question, and then we'll briefly go over the bonus. Let me pull my compass out real quick. A lot of people were doing too much work for this question. They were constructing the center of the circle. You don't have to do that because they already give you the center of the circle, right? It says circle O. Circles are named for their center, and the center is right here marked in the diagram. So don't do more work than you have to. It doesn't add anything if you do more work than you have to. So what I'm going to do is I'm just going to open up and make a little arc here to get me started as best as I can. I hate using the compass on the computer. I think it's awful. Actually, what I should do, let me try that again. I'm going to draw a radius. There we go. Then I don't even have to think. I'm going to start by measuring the length of the radius. Let me do that as best as I possibly can. Once again, I hate using the compass on the computer. Okay, that's as best as I'm going to get it. Okay, without changing how far my compass is open, I'm going to go to that point and make an arc. Then I'm going to pick up and move without changing the radius of my compass. Let me get some more space here. Okay, that looks about right. I'm going to be a little bit off because this is on the computer. It's not wonderful. There we go. Let me tilt this a bit. Now I got to move my screen up. There we go. Almost there. Just a few more arcs. Let me try to move my screen up even higher. There we go. Okay. And this is my last one, so it should put me back where I started. Awesome. Great. Perfect. Okay. It's a little bit off, as I mentioned, but it's as good as it's going to get using this computer compass. So let me connect all these points together. So let me connect this point to this one to this one, to this one. And remember, we want the points to be on the circle. That's the whole point. It's supposed to be inscribed. The hexagon's supposed to be inscribed in the circle. So the vertex points should actually be on the circumference of the circle. Some people weren't doing that, and then it's not right. Okay, so that would be 3 points right there for this question. Constructing the hexagon, that's it. So now I'm just going to label according to the question. So it says to label it A, B, C, D, E, F. Beautiful. Okay, now it says in part 2, chords FB and FC are drawn. Let me get another color for my line. So chords FB. So here's F and here's B. And FC are drawn. So here's F. Now it should be, I drew that line really poorly. Let me get my line back. FC. Should be on the same level. Let me move mine up. It's not on the same level as C. Sorry, this computer is awful. There we go. Okay, I think that's clear enough that we can see what's going on over here. Okay, yeah, I think that's clear enough. Okay, so it's asking what kind of triangle would triangle FBC be? So just so you can see what FBC is, I'm going to just outline the other side of that triangle in purple as well. So it's the triangle that's now in purple. And the thing that's jumping out to me is I see that there's going to be a right angle. And it does say classify according to its angle. So isosceles, scalene, equilateral, that's not really what it's looking for in this question. So I give a point off if you said that and explained why, but it's, it's not what the question's asking for. So I see a right angle over here. And the reason that it's a right angle is because angle FBC is an inscribed angle of the circle. And it intercepts a semicircle, a 180-degree arc. And we know inscribed angles are half their intercepted arcs. If the intercepted arc is 180, half a circle, the inscribed angle would be 90. Let me type an explanation for that. Let me just make this smaller. Here we go. So triangle FBC is a right triangle because angle FBC is an inscribed angle that intercepts a semicircle. So it is a right angle. Here we go. And where is the bonus? There's the bonus. So we're constructing the incenter and incircle of triangle ABC. So the incenter is where the angle bisectors meet. And technically, to be as accurate as possible, we should construct all three, trying to get the compass back, all three angle bisectors for the three different sides of the triangle. But I did take it if you only did 2, because technically you do only need 2 to see an intersection. But doing all 3 would make this as accurate as possible. I'm going to try to do all three because I want to get as accurate as I possibly can. So all I'm going to do first is I'm just going to make an arc. This is not going to be accurate anyway because I'm using the computer. And I'll just open it up a little bit more. It doesn't really matter how far you open it to do an angle bisector. What matters is that now you keep using the same hole or the same, distance that you opened your arc to. I'm just also trying not to make my arcs so crazy big because if I do, it's going to be insane. So there's the intersection. Make it a little bit long so we make sure to see the intersection with the other angle bisectors. Okay, let me go to one of the other angles now and bisect that. So I want to bisect angle B. Once again, I don't really want to make these arcs so huge because I want to be able to make sense of my work here. Let me open this up a little bit wider. It doesn't exactly matter. Okay. Let me put my point on the other intersection point. There we go. And right through that intersection point. Okay. And I'm just going to bisect the last angle. I already see where the point's going to be. Oops. Let me undo that. But doing it for the third one will get the most accuracy, the most precision. And we do aim for precision in geometry. We want to be as precise as possible. It doesn't always happen, but we try to be as accurate and as precise as possible. Geometry is all about precision. Okay. Those arcs are a little bit bigger than I wanted them to be, but that's okay. Let me move over here. Just want to make sure that I see the intersection. There we go. Not crazy big. Right through that intersection point. Oh no. I cannot draw lines on the computer. I am not good at that. Let me try to fix that one because I did not draw it where it's supposed to go. Let me get rid of it and start again with that one, with drawing the line. Ah. No. Okay, as you see, it keeps jumping around. So let me dot where it should be. So it should be where they all meet, which is about right over here. So in order to accurately make the inscribed circle, the in circle, what I need to do is actually construct a perpendicular line through the incenter. So we found the incenter, it's where the angle bisectors meet. Now we gotta construct a perpendicular line, so that could be the radius of our in circle, so that, it actually is inside the walls of the triangle. And once again, we're aiming for as much accuracy as we can. So I'm gonna take my compass and I'm gonna put it on the incenter. And I guess I'll use green. Let me get more space down here. Okay. Now, it doesn't matter how far I open my compass. Oops, that wasn't far enough though, because we do want our arc to hit a side of the triangle in two spots. Notice how there's two intersection points now. So what I'm going to do is I'm going to just take my compass. I'll move over to one of those intersection points. So I'll just go over to this one first. It looks more messy. I'll get that one over with. I'll open a little bit farther and just going to make an arc. There we go. I'm going to go over to the other intersection point as best as I can. And I made an arc so that they intersect. Okay, I'm done with my compass now. So let me get a different color line so we can actually see that perpendicular line. There we go. So this line is a perpendicular line through the incenter. So we're actually going to use that as the radius of our incircle. So let me get a different color on my compass. Use blue for the incircle. I'm going to put my compass on the incenter as best as I can. I can't really see anymore on this computer. Okay. And then I'm going to just open up to the length of the perpendicular line as accurately as I can. And then I'm going to string my circle. Oops, I don't think I opened that up wide enough. 1 second. Let me fix that. Give me 1/2 a second. Okay, finally got it lined up there. So as you can see, we're not 100% accurate. It should be touching the walls exactly inside the triangle. But we try to be as accurate as we can on this computer. I can't be very accurate at all. I much prefer to do constructions by hand with a compass that I can hold. But the important thing is here that is that to construct the incenter, it's where the angle bisectors meet. And then once you have the incenter, once you have that point where the angle bisectors meet, that's going to be the center of your incircle. But in order to find like where the radius should be, you do need to construct a perpendicular line through the incenter, and that will be the length of your radius of the circle. So you'll put your compass on the incenter, open up or find the hole that matches up to the end of the perpendicular line, and then swing your circle all around. And it should come very, very close to exactly hitting the walls of the triangle.